Let's begin this example by discussing three different kinds of discontinuities. The first one is the removable discontinuity, which we have here in the top two examples, which is a graph, right? So these are explained graphically, but in the graph of these, it's a single point that if you could plug that one point, it would be fixed, right? So in this first graph, we're just missing a point, but imagine if we just plugged that in there, it would be fixed, right? One point fixes the whole thing. Same thing with this second one. We have a point, but it's in the wrong place. But if we just moved this down and replaced the missing point, it would be fixed. So that's what we mean by removable discontinuity, easily fixable. Down to the bottom row, we have a jump discontinuity, which is more problematic, right? There is no fixing this. We could put in a different point, maybe somewhere in the middle. It doesn't fix it, right? So this one is fundamentally broken. They just don't come together. The function jumps. So it's really inherent in the name jump discontinuity. It really paints a picture of what it is. So that's a slightly more problematic discontinuity. And then finally we move to the last one, an infinite discontinuity, which is essentially an asymptote, like asymptotic behavior of some kind, right? And that's really not fixable, right? There's no plugging in a point to fix this. It is very discontinuous, and it's worse than even a jump discontinuity. So there's kind of degrees of discontinuities that various functions can have. For this particular example, let's focus on a removable discontinuity and then work on fixing that so that the function becomes continuous. Here we want to find a value of a that makes the function continuous, and we're given a piecewise function. As long as x does not equal -1, we have x squared plus 3x plus 2 all over x plus 1. But then when x equals -1, we have a, and that's what we're trying to solve for. Well, remember that we have the continuity checklist that tells us when a function is continuous. F of x is continuous at some point c if the function at c is defined, the limit as x approaches c exists, and the limit as x approaches c of f of x equals f of c. So we'll focus on number 3 for our interest here in this particular example. We can evaluate the limit as x approaches -1 of the rational function x squared plus 3x plus 2 all over x plus 1. Okay, well, if we just plug in -1 here, we get 0 over 0. So let's see if we can do a little bit of rearranging here. So still have a limit, of course. X goes to -1. This factor is always looking for something to factor here, or x plus 1 and x plus 2 over x plus 1. X plus 1's cancel. And then finally we can just plug in -1 here and we get 1. So as x approaches -1, the function is approaching 1. What we're left with here is a function that is essentially a line, except for it has a hole right here at -1. So let's see here. It looks something like this. Comes up like so. Hole, and keeps going. And this is at -1. And so what we can do to fix this is just plug that hole by saying, okay, right at x equals -1, I'm going to fill in this hole by letting the function equal 1 right there. So essentially what we're saying is f of -1 equals 1. We're just defining that to be the case. Back to our piecewise function, this is equivalent to saying a equals 1, right? That makes the function nice and continuous, and everything works out.